So this is a session for how to run your first regression using R and Stan. Okay. Now just understand, Stan the engine behind your Bayesian modeling or analysis, but you cannot directly use Stan, or there is a way to use it, but I do not know. So use R to to so you put the information in R, and R is able to translate your information to Stan. And same way when Stan does it, it talks to R, and R. So using R, we print things out the way we want the results, right? The coefficient and things. So understand that. Now, for one of my student, what I have done is that I have sent the data set, just a dummy data set, and the data set had four independent variable. It's a energy sector. It's all in log. So log OPEX is a dependent variable, and these four are the independent variable. And look at this result. This will run in data. Okay, just simple regression. Now I'm going to show you how you can actually do in R. So your data, you can look at the data here. This is the data that we have. This is what we use to fit the regression. So have a look here. So it's kind of a, what do you call it? It's a panel data. Okay. So, what is the first step? So, this is your R, right? I'm just saving is that Stan simulation. So, you can go to File, Save As, and type this name. So, this is your first Stan. You can name whatever you want, your first Stan regression or whatever. What is the first stage? Now, first stage is we just need to add a couple of libraries, okay? So, that means we'll be using some special package which is already in your uh, R. You just need to call it from the library. So this is it. So library bracket CMD Stan R, library posterior, and library read Excel. Read Excel is basically to import your data. Now, what is the code to import your Excel data? This is basically what the code is. Now, this is very simple, right? So I have already made the code here, but very simple. So nothing too complicated. You just go to File, and this is our import. So here is a Excel data. You go to Excel, just untick that. You don't need to view the data. So you just untick that and the browse here. And then we have our data here, right? This one here, right? Data simulation. So look, if you click it, you get this code. This is a code, basically the code that I just pasted here. So in that way, I don't need to go each time like this. I can just go here and run it. It will import the data. So let's do that, import the data. Okay, it's done. Now it is the next stage. Now, I need to assign dependent and independent variable. Now I can give whatever name I want. For dependent variable, I just want to name why? Because the data is sitting in this Excel here. I need to sort of separate them into independent and dependent, right? And then I put in a way that Stan understands. So I'm just going to give dependent variable y. You can call whatever you want. You can call ln opex if you want to. It doesn't matter what you write on this side of story. And now here, what happened? This is your data set. And as soon as you put dollar in here, it opens up. For example, have a look here. If I put a dollar in here, see, it opens up all my details. So my dependent variable is OPEX. So that's the way. So that's my Y, right? Right. And then you got your X1. That's the first independent variable, which is ln capex. Second independent variable, which is ln length. Third independent variable, which is ln number user. Fourth independent variable is data simulation. Is the ln energy that comes from the data simulation Excel sheet we just imported, right? Is that okay? So right, so you got one independent variable. So this is your independent variable here, and this all is your dependent variable, right? Beg your pardon, sorry. This is your dependent variable, and this all is your independent variable, right? Four independent variable. Now, what is the next step? Now, see what we're doing. We are putting all those independent variable in a I can call that as a matrix, right? Let's have a look what it looks like. So if I use this command x, a big X, right, is equal to C bind. I think it's column bind. It binds all the column together. This x1, comma x2, comma x3, and x4. And I try to run it. I think it just puts all the columns together. Let's have a look. Oh yeah, it's just columns together, right? So it's all those four columns together. So it has four columns: one, two, three, four. Four columns, and there's 250%, lots of rows, right? That's the way. So it just puts the column together, right? Now we just now it's the thing. Now we created extracted data, put it all in a matrix. If you want to say X is in matrix, X is a matrix, so it's a independent variables matrices or matrix. And next step is we need to put the data in such a way that it it can be input into Stan. So what do? We create a list of data. We can name anything you want. So have a look here. So you can name whatever you want here. This is like equal to, R can either take this or it can take this. And then use the word list and open the bracket. What is the first thing it does? It N. How many rows are there? So that is, you can take Y, which is just one column, right? So if you look into Y here, it's just your dependent variable, which is just one column. It's just one column and has got so many rows. If you just work out length of Y, it will tell you how many. For example, if I take the length here, close the bracket, 511 rows. So my number of observation is, if I say N is equal to length of Y, it will give you number of observations I have, right? So R require all these things, right? Sorry, Stan requires number of observation, number of columns for the independent variable or the matrix that we created, all that is needed. X, what is my independent variable? I name it X, and that is X itself, right? So I put that X in together and I can just name here X. You'll see why I'm doing that, okay, later on when I get the Stan code here. And then you got P. So n column means how many columns have. So if I say P is my number of columns and I put X in the bracket, it'll count the column. So if you think about this, how many? We have 4 columns, right? So Control C, I'm just going to do it here. So 4 columns, right? So in Stan needs to know how many observations you have, how many columns you have, how many rows you have, and what variables you have. That's why we're putting that in the list. And our Y is our dependent variable, which is just a column vector. C in the Y from here and put in the column vector, right? You can name different variable for here. You can name something else here, Z, and this you can have whatever a small y, but I just find it easier to keep it same because this is how the variable will be read in the R command that you have to run the model. This is simply putting in a list of data and other information that R Stan needs to run the model. Right, close the bracket. Brilliant. Now, here we go. Now, this is where our code comes in. So it always starts with call. We put it get a inverted comma here, and then we write our code in here. We give a name a code because different models have different codes. So we call it stand code 1 or stand code, regression or whatever. Don't forget this. And then first, this is how the stand works. Okay. So first is your data block. What is the data block and what are those things here? Now you don't need to worry too much about this because once you have a model, you can just keep using it. Just change the variation of your modeling what you need. But this is the basic, right? What we are saying, n. Remember this n is a number of observation you have is an integer with a lower value of 1. That means it starts from 1 all the way until and there is n number of observation. It starts from 1. So when you have a look at this length here, let me just show you. When you look at this length here, it says 511. So it's just simply saying there are 511 observations or rows, and the minimum one is 1. It starts from this. The lower value is 1. Second is P. Now P, remember how many X I have? I worked out there's 4 independent variable, right? So that's why I say count the number of columns because we put this in a column, right? Putting all those columns together. And that P also starts with 1. That means we got 1 all the way to P, which is 4. So that 1 is the minimum and then 2, 3, 4, right? And then you have your predictor matrix. So this is this X, right? This X we bind and we put that X here. That means it got n observations, like how many observation you have here. And we have counted out 511. And P, that is how many columns they have. So this is a number of rows and this is a number of columns, and that's our matrix X. This is exactly the way you create it. For example, if you have a look at this X here, see that? This is a matrix. So this is the n here, the rows, and this is the p here. So that's what you put in the matrix here, right? Right. And this is your dependent variable. Dependent variable is just a vector or column vector, what we call it. It got n in there, but there is only one independent variable, so we don't need to put a p in there, right? So you just put y in there. You understand the data block part? This is very, very important. Now we have the parameters. The parameter is what you want to estimate, right? So you want to estimate the constant value, like real alpha. For example, this one here, this is a constant here, right? So you want to estimate the constant as well because that's the unknown. And you call it real alpha. Why do you call it real alpha? Real means that it can be a positive or negative value or zero, right? That's what you put the real in there. Now, after this, this is beta. Beta is your coefficients. How many coefficients you have? You have one, two, three, four, because you're four independent variables, four coefficients, right? So you have, you're saying that beta is a vector of p. So how vector of p? So p is four, isn't it? So it's just a four vector, right? It's just four values basically. And then you have your sigma. Now, sigma is something in this regression you perhaps might not be able to see it. It's like a think I don't really remember particularly, but I think it's like a standard error. Somewhere here, it's mean squared. Yeah, I'm not no. It's basically econometrically. I don't know if Stata provides it or not. It's like a Bayesian frequency is quite different, but basically what you need to think about that this sigma is the standard deviation of the error, right? You understand this idea of standard deviation of error, right? So, for example, let me just get the paint here. That's the best way to teach you guys paint. So, you have your y, which is, your regression classic here. You got b naught plus, this is, the coefficient, then you got x, and then you got your error, right? Now, what we assume, the error is normally distributed with a zero mean, and we call it standard deviation of the error, right? And that standard deviation is what we have to estimate as well, because that's very, very important. Because the whole idea frequency statistics does is that minimizes the error, right? So the variation is minimized, but we don't do that here. But I just want you to think about it. So when this happens, when you make the assumption that error is normally distributed, right? What happens is then is your y actually becomes normally distributed, right? With the mean of the normal distribution becoming x, right? And the standard deviation becomes this. So just because we are making the error normal distributed, we can write like this. This is the, because of this error is normal, we can actually write y is also normally distributed with the mean with the regression part, and then the error standard deviation is a deviation. Remember in regression, you remember probably when you were studying your first econometrics paper, right? It's the mean value and average is what you predict, right? So this is sigma. Now, why do we put the lower? That means it is minimum it can go is zero. That means it cannot become zero. It stops there because it's always have to be positive. Standard deviation always have to be positive. So we'll look at limit in there. And now comes your prior. You remember all your prior, what the priors are? Priors are something that you think is the parameter value will be. You specify, uh, whether you want a wide prior or, or a short prior. So here what we're saying is your sigma here is exponential. Now, one of the things about the exponential distribution is, now have a look at the exponential distribution. Why am I saying prior is exponential? So exponential distribution here. So what is exponential distribution? Have a look at exponential distribution here. See, exponential, you take the x value of x and notice it cuts off here at zero. It doesn't go any less than zero. So exponential might be a good prior. So let's assume that our standard deviation comes from exponential distribution. Now, exponential distribution 2 basically means that so what is the, let me just bring that, why I'm saying exponential to, so exponential only got one parameter, normal got your mean and standard deviation, right? For exponential, you got just one parameter called lambda, and lambda is greater than one. Just like, just like your normal distribution, mean and standard deviation, exponential and kind of distribution, just got one parameter called lambda, which cannot be greater than zero, which cannot be smaller than zero, right? It has to be greater than zero. What is the mean is equal to 1 by a lambda here, right? Does it make sense? So what is my lambda here? 2. So what will the mean of the distribution offering as a prior? 0.5. Yeah, that's fine. Why am I saying 0.5? Now, this is where we can actually use our sense. Now, think about this. So you have your y here, right? So if I work out, have a look here. What is the standard deviation of y? Let's have a look. Is 1.22. Okay, so y varies by 1.22. So you can have a exponential prior 1, that means 1 divided by 1, the mean will be 1, so most of the value will be getting only 1. But I don't want to do that because it's a log variable. I think standard deviation will be pretty small, so I just put that 1 point, sorry, I'll just stick with my 2. And then beta. Now remember, this is a log variable, and when you take the variable as log, this is all the variables are logged here. When you take log, the coefficient of a production function becomes what? It becomes percentages. So I'm saying that, okay, beta can come from a normal distribution of 0 and 2. Remember what the normal distribution was? What is the one of the criteria for normal distribution was? I taught you guys normal distribution spread like 68% and all that sort of stuff. Right. So, oh, that's good. I got it right. So remember, when you got a normal distribution, right? See that? So if I specify a normal distribution 0 mean, 68.27% approximately will be 0 plus 1 standard deviation, right? Then the 2 standard deviation. Now here, have a look here, what my prior is. My prior is 0 and 2. So 68% of the data will be between 0 and 2. And 95% will be between 0 plus 2 standard deviation, that is 4, will be 0 and 4. You understand what I'm trying to say? So you specify prior that my value coefficient is actually coming from the that sort of prior. Alpha, I'm spending a bit more small prior because of the intercept, but it's up to you, right? Now some people have a wide prior, some people have a pretty short tight prior. It's really depends. Now you can never do this. This is wrong. So you already run the regression using frequentist data, and they say, oh yeah, variable and use according to prior. No, no, no. Prior should be your knowledge, that what you know about it. When you take the log, the coefficient of particular variable. For example, let's say length is not going to be 500, is it? Because added together, they might be up to 1 or slightly over than 1, right? This is what we call the increasing decreasing return to score, call it. Now this is our prior, right? This all is our prior. This is our likelihood. We call it data likelihood. We'll tell you more about it, but just remember for the time being, because of this error here, we make y and we write exactly like this in our state, in our stand, I mean. And you close that. See, this was a model parameter, model block, and this was the parameter block. We declare what parameter we want and model this here with the prior and likelihood. Generate quantities, you'll learn a little bit about that later on. Don't worry about it as it. And then you close this inverted comma here. So your stand code is set. Now to the next step now. Now you need to just compile the stand code. That means that you just, see if everything is correct. If there's some error, it will tell you if there is some error, right? So what do we do now? So you just give a name here that my stand code is in the model, and this is just have to use this. This is the code. Write stand file stand code 1. This is stand code 1 here. Just use exact like this, the syntax like that. Run that, and I'm just gonna select it and run it. Model executable is up to date. This is the good news. Now let me make an error, okay? Let me just say I put here sigma u, but I haven't declared sigma u here. So let me just see what error it throws up. It should throw up an error because sigma u is not declared in the parameter block. So it's trying to run. It's trying to compile it, not running, compiling it. Identifier sigma u not in scope. Did you mean sigma? Yes, I meant sigma. Does it make sense? So yeah, star will give you error. Now, if I miss this, for example, this one here, this dot comma, I missed that. See, Stan will do the same thing. So make sure you select all of it from here, right? Yeah, see that? I accept that. So that wasn't there, so we put that in there. And now what will happen if somebody just put real sigma? That means, oh, sigma can be anything, it doesn't have to be a positive value. Well, that's a bit useless, isn't it? Because it has to be positive. It might not create any problem here, but we run the model. But just keep that in mind, right? I don't think it might create any problem because it's not a syntax error. So might not create anything at this stage, but it will in the future. So it's just compiling it. Compilation just checks for the syntax error. Okay. Yeah, that's because you got an antivirus, but now you will not have that problem. So let's have a look. So just correct all this. This is all good. This is all good. Now, this is where you tell Stan what to do and where the data is. So have a look here. Right. So you run it. So it's all ready to go. It's all executable. Now, you create something called fit1 where Stan will, store all the sampling thing that you do from the model, and then you, of course, like equal to, you put that. Then model one. Remember, this one here is the previous code for our model is, and you write it, check it, and the corrected code, compile code is stored in there. So you say, go to this code, this compile model, and sample from it, right? Sample. You don't understand what the Bayesian is, right? What do? When you specify a model, it goes and get the samples, right? So it doesn't minimize anything. It's not about minimizing error as you learn econometrics. It goes and takes the sample. So what it does, it takes the prior. It says that, okay, I know beta is between normal distribution, with a mean of 0 standard deviation of 2. It goes in there and takes a part of that value from it, and then it goes and looks at the data here. See, we got this data. So it goes and does this, and it gives you the sample of betas. So you'll not get one beta value, you'll have, depending on how many sample you say, get the beta. I will give you more information about this, about the Bayesian thinking later on, but just think about it. Take sample. So it will give you 10,000 betas, and you take, if you want to know one value of that, you just take a mean or median, whatever, right? This is the thing about the Bayesian. It doesn't give you one value, it gives you a distribution of everything, right? So here, for example, your alpha will have a distribution, your beta will have a distribution, your sigma will have a distribution, right? So one of the benefit of Bayesian. Now, what do? So you specify first your data, okay? You model this, sample it, but where is the data? So I name it. This is some names you have to. This is a syntax for running stand through R. So data is in the data list one. Remember the data list one here? We put it all in here, there, and then chains is equal to 4, right? Four chains. What does it mean by that? Just think of this as this. There are 4 people who are you setting out for this adventure of getting the sample. You tell them some prior so they know where to look for, and then 4 different people you send down and ask them to get samples going in the jungle, or whatever you're going to say, for alpha, beta, and sigma. And whatever they bring back, right, you take average of all those average, right? So one person big 10,000 sample, you take an average of that. Suppose you're looking for alpha, you get one alpha, and then you take the average of second, third, fourth, and then you got 4 averages. Then you combine of the average, you get the mid, right? That's one way to do it, right? Because we like to work with one number rather than distribution. Okay, so um, then parallel chains 4, that's just a more computer thing that you want to run 4 at the same time. Refresh 25 means you want to see your progress of how many. So, if you're, for example, here you're saying that you want to sample 1,000 samples for each parameter. So there is 4 here, right? 4 chains. So 4 times 1,000 will be 4,000 samples, right? That will be sample. And then there's iteration warm up. Warm up of 1,000 means something like, it is also a sample, but in that first, so altogether it will do 2,000 here, right? 2,000 plus 4 is 8,000 sample. But we sort of don't take into account the first, because I'm specifying here that do a warm up of 1,000, and next 1,000 is what I want you to sample. Now, first 1,000 is warm up. What it means is that those soldiers or those people you're sending out, those 4 people, sort of prepare themselves very well. They check everything and they see where in the world they should actually go to actually get the sample, right? To get the most appropriate sample for our model. That's the whole idea here. So this is what here, that's the idea. So altogether, you're going to get about, basically we'll be working on this 1,000 sample times 4, that is 4,000. Okay. Now, this is here. What do? You go here. Yeah. And you try to run it now. Yeah. See, forward child is running all the, so it's saying 2,000. It's running your chains. It's pretty quick here because it's not very complicated, but not as quick as Stata, because Stata isn't sampling, this is sampling. Okay, all chains successfully. Don't worry about the warning quite yet. And now I want to see the result. So have a look here. So I'm just going to the game draws my fit. Get the draws from this fit one, because fit one got all your sample here. And I'm saying I want to see the variable beta and sigma, and then I try to run it. Yep. So that stored that value. And then I want to see 90% credible interval, just like a confidence interval, 90% credible interval, not exactly that, but for the time being, understand. And this is the code for that. So you summarize the draw. I talked about the mean and things like that. I want to see. So my data is my parameters alpha, beta, and sigma are stored here, right? In draws fit one. I ask it to go in draw fit one and summarize my draw. I want to see the mean of the distribution. Remember, it's all the samples, and with the sample you have a distribution. I want to see quantiles. Basically, this is 90% credit on draw. I want to ignore the first five and the last five. I want to see the middle part, right? That's what I'm trying to say. And then these are two different, these are things you will learn later on. Basically, what you want is that you want a lot of sample here, and you want r hat close to one. That's so it's like a test. I'll show you. So let me just run this. Fair, that's good. And now you want to print it, right? You want to see it. So this fit one is stored all the summary and you fit it. Right. So 95% increment tool says that 90% of the time your beta 1 parameter will be 0.499 and 0.6. See how it gives you the distribution, it gives you the 90%. Now this is very different from confidence interval, which I'll explain to you later on. And these are our parameters, right? Alpha parameter, beta 1, beta 2, beta 3. So beta 1 relates to, see what was your first variable? Beta 1 here, right? It was ln caps. So ln caps coefficient is 0.59. And this is your error deviation, right? And we done that. And this is here how many samples you have. This is pretty good, right? Basically you want samples, greater than, there's no certain number. The better, more you are, the better it is, at least 500 and above sample, but better. And these are all close to one, which is good. You don't want anything higher, like 2 or 3, close to 1 or 0.99 is what you want. Now let's check how does that looks with the what we already been done. So my alpha is, let's have a look. Alpha is constant is 0.98. I got 0.64. ln energy, capex, let's have a look. It's 0.5589. We got 0.59 here. ln length is 0.03. We got 0.01. And number user is 0.342, 0.399. Beta 4 is minus 0.317, now 0.2. So slight differences, but that's not a big issue at all. So don't need to worry about that. Slight difference is expected. So see this here, root mean squared error. So I think this is what this sigma is here, root mean squared. Right. So now significance. So ln capex here is 0.559 and p-value is very small, so it is significant. You will notice here 0.59. Here also, see the credible interval here. 90% credible interval does not contain zero. So we have no chance of getting zero. So we can say that it is significant, right? Even though we don't use the term significant in Bayesian, but that's what you can actually say. Beta 2, 0.03. See that? It's 0.42, not significant. And here you notice it's from minus 0.3 to plus 0.6. It includes zero. So we can say we don't know. There's 90% chance that it might have zero as well. So you say that's not significant. Beta 3, 0.34, very small value. Here also, credible interval is between that, no zero, so it's significant. Beta 4, minus 0.2, not significant. Minus 0.03, minus 0.102 to 0.04. That is also contains zero. So, yep, it's not significant either. Constant minus 0.9, and that's not significant either. So that's what we got minus 0.64. It includes zero. Yeah. Does that make sense? So this is what it is. So try to run this. And what I'm doing that just as you go, make sure that you try to type this yourself because it's important that you get the practice for the first time. So I'm not going to send you this code. You have to type it yourself. Okay. So let me just slowly take it down here. Just follow this process. This code here. Type all yourself, Giovanni. And any other students who are watching this, right? Can I make it a bit bigger? View, zoom in. Yeah, here we go. Okay, just I think here was my videos. Type all this because I want you to do this, and you should make mistake to understand this. Okay, all right then. Brilliant, sensational. Let me just stop the Recording.